Hello everyone. Today we are going to discuss the problem course schedule from CSES Graph problem set. Let's go through the problem. You have to complete n courses. There are m requirements of the form course A has to be completed before course B. Your task is to find out the order in which you can complete the courses. Input is in this format. The first input line has two integers n and m, the number of courses and requirements. The courses are numbered 1 to n. After this, there are m lines describing the requirements. Each line has two integers a and b. Course A has to be completed before course B. You need to print an order in which you can complete the courses. You can print any valid order that includes all the courses. And if there are no solutions, you need to simply print impossible. So this is what the problem is. Let us first of all try to understand the problem with the help of the input given, and then we will see how we can actually solve this problem. So in the input, we have 5 courses and there are 3 requirements, and the requirements are that A to B means course A has to be completed before course B. So over here the input says that 1 has to be completed before 2. So let me just write it down over here. What are the requirements? 1 has to be completed before 2. 3 has to be completed before 1. And 4 has to be completed before 5. Okay. So there are in total 5 courses and there are these 3 requirements that we have. Now, just to understand the problem better, what I will do is I will convert this problem into a graph. Okay. Like 1 has to be completed before 2. By this, I would mean that there is an edge from 2. There is a directed edge from 2 till 1. Or just a minute. Yeah. 1 has to be completed before 2, right? This means for completing 2, there is a dependency of 1, right? So we will draw a directed edge from 1 to 2. Okay. Similarly, it says that 3 has to be completed before 1. This means 1 has dependency on 3. So 3 has to be completed before 1. So I draw an edge from 3 to 1 with the edge pointing towards 1. That first of all I will complete 3 and from there I will go to 1. And the other requirement is that 4 has to be completed before 5. So I draw a directed edge from 4 to 5. You need to print any valid solution. Let me just take the output given. The output given is 34152. This is the output given, and let's see whether this output satisfies all the requirements or not. The requirement was that 4 has to be completed before 5. Yeah, this is getting validated. Another was that 3 has to be completed before 1. Yes, this is also getting validated. Another requirement was 1 has to be completed before 2, and yes, this is also getting validated. So yeah, this is the correct ordering, isn't it? Cool. So this is what the problem is. I hope the problem is clear that if you are given m requirements, you have to satisfy all m requirements and print any valid solution. If there are no valid requirements, you have to simply print impossible. Like for example, in this particular problem, this is also a valid requirement, right? Like 31452. This also satisfies all the m requirements that you have. This is what the problem is. Now for anyone who already know what do we mean by topological sorting, and I've heard of algorithms like Kahn's algorithm. For them, this problem is very straightforward. Like this problem actually wants you to topological sort it. So this problem is a straight implementation of topological sorting. But for the people who don't know, I would try to give some context of what do we actually mean by topological sorting. You can do topological sorting via a simple DFS as well, or there is a very famous algorithm named as Kahn's algorithm as well. So what do we actually mean by topological sorting? Let me try to give a bit of context on that. Let's suppose you have a node A and it tells that node A has to be bought in before node B. Like there can be multiple nodes in the graph. Let's suppose node A, B, C, D, E. And there can be some directed edges like this. Like there can be edges like this, there can be edges like this, there can be edges like this, there can be multiple directed edges. By topological sorting, we mean that we arrange the nodes. We arrange all the nodes of the graph in an order such that if there is an edge between A and B, if there is an edge between node A and B, node A and node B, and the edge looks something like this. There is a node from A to B, node between A and B, or I would have written node between A and, like, node from A to B, something like this. Then A occurs before B in the ordering. In this way, if you are able to arrange all the nodes in the graph in a particular order, then you say that the graph, that this is a topological ordering order. And if it is not possible for you to do so, you can say that graph cannot be topologically sorted. For example, if let's suppose I would have told you that this is the graph you have, this is node 1, this is node 2, this is node 3, and this is node 4. Sorry, this is node 3. Yeah. So if I would have told you that for 2 to come, first of all, I have to write 1. For 3 to come, first of all, I have to write 2. And for 1 to come, first of all, I have to write 3. So you can definitely see that over here you have a cyclic dependency. So you can't form any valid order, and hence topological sorting is not possible. So this is what topological sorting actually means. Now, how do we actually do this? So there is a very intuitive and very easy solution to this. And the solution states that take the node. Like I often say like this, only take the node you can take. What do I mean by that? By that I mean is, let's suppose you have this particular graph arrangements, node 1, node 2, node 3, and node 4. Let's suppose you have this particular graph arrangement. Over here, can you point out for me the node that is not dependent on any other node? Can you point out that node for me? Yes, you guessed it right. Node 1 is not dependent on any other node. Node 2 is dependent on node 1, node 3 is dependent on node 2, node 4 is dependent both on node 2 and node 3. But node 1 is not dependent on any other node. So what I will do is, first of all, in my ordering, I will simply keep node 1. Now once node 1 has come, can I say that all the nodes that were dependent on node 1, for them the job is done? Because till now they haven't come in the ordering and node 1 has already arrived. So now they are not dependent on like this edge. This edge now makes no sense because node 1 has already come. So now 2 is not dependent on 1, because anywhere in the ordering when I will take 2, it will come after 1 only, right? So now this edge is not a blocker for me. So what I will do is I will remove this edge. Definitely we don't remove the edge while we are coding it down. But the basic understanding is that we will remove the edge. We will see how we actually remove this edge. But for now what I will do is I will just simply remove this edge. Done. Now tell me the node. Tell me the node. This one has already been taken. So I will just remove this. Now tell me the node which is not dependent on any other node. Yeah, node 2 is not dependent on any other node, right? So what I will do is I will simply take node 2 as well in the ordering. And I will remove node 2, and since I am removing node 2, so all the nodes that were dependent on node 2, for them that particular edge will also be removed, right? So I am removing node 2 and this thing. Now tell me the node that is not dependent on any other node. It's node 3. So now I will remove node 3 as well, and this particular edge as well. And then the leftover node, that is node 4, comes, and here is the topological ordering for the graph. So this is how actually you write topological sorting. Now, how I was able to see that whether a particular node is dependent on any other node or not, how I was able to see that? So for that, I will just redraw the graph that I drew, this 1, 2, 3, and 4. So what I will do is, for each and every node, I will maintain in degree for that node. What do I mean by in degree? From node 1 to node, for node 2, what is the value of in degree? In degree means number of edges that are pointed towards that node. So for 1, the in degree is 0. For 2, the in degree is 1. For 3, there are one edge that is pointing towards 3, so in degree is 1. And for 4, there are two edges pointing towards 4, so in degree is 2. So I will calculate in degree of every node. Now, the nodes having in degree 0, what does it implies? It implies that that particular node is not dependent on any other node. So I can take them in the ordering. And once I take them in the ordering, once I take one in the ordering, all the edges that goes from 1, like this particular edge was going from 1, right? So for all the nodes that have an incoming edge from 1, for them the in degree will get reduced by 1, right? So once I take this particular node, what will happen is the in degree of 2 will now becomes whatever was the in degree minus 1, because this particular edge will now vanish because 1 has already arrived. So I will simply subtract 1 and you will get 0. So once you get in degree as 0 for any particular node, you take them in the ordering and perform the same steps. So to do this step by step, we simply use a queue. You can do it simply by a DFS as well. I am going to code it by Kahn's algorithm, so I am going to use a simple queue. So this is how you actually solve the problem. I am not taking more examples because my main aim is not to discuss what is topological sorting and all. I gave you a bit of context of how actually it works. It is very intuitive. Even if you don't know this algorithm, this question can be solved. And this is how you actually solve this problem. Okay. Let me go through the code once so that you guys understand it better. So I'm taking the number of nodes and edges as input first of all. So calculating the list and the in degree for every particular node, taking the input u to v, converting to zero based indexing. There is an edge from u to v, so adjacency of u I am pushing back v, and I am incrementing the in degree of v by 1 because there is an edge from u to v, so for v there is one incoming edge. Now I construct a queue and a topo order vector. Going over all the nodes, if the in degree of node is 0, I am simply pushing it in the queue. Now while the queue is not empty, taking the node, popping it, pushing it in the topo order vector, going over all the neighbor nodes of the adjacency node and reducing the in degree of that neighbor node by 1 because this particular node is coming now. So all the edges that goes from this particular node, and for all the nodes that have an incoming node from this particular node, for them the in degree will get reduced by 1. And after reducing by 1, if the in degree for that neighbor has become 0, this means that now I can take them in the topo order vector. So for that I simply push them inside the queue. Once I am done with this, and if my topo order size is n, this says me that I was able to take all the nodes, so there was no cyclic dependency, and hence I am simply printing, if the size is not equals to n, this means I was not able to take all the nodes. This means there was some cyclic dependency and hence topo order does not exist for this particular graph, so simply printing impossible and returning. Otherwise, going over all the nodes, printing node plus 1. Node plus 1 because I am converting it to 1 based indexing. The output wants me to print in 1 based indexing. So this is how you actually solve this problem. A very classic implementation of topological sorting. Very, very important algorithm. So yeah, you should definitely learn this. Okay. I hope you guys understood it. Thank you.